light can cause matter to rotate. That statement sounds incomplete at first, almost unfinished, because nothing in it mentions mass, impact, or contact. Yet in 1936, Richard A. Beth demonstrated exactly that effect, using a beam of circularly polarized light and a torsion balance sensitive enough to register the smallest twist. When the polarization was reversed, the rotation reversed with it. When the beam stopped, the motion stopped. The exchange was direct, repeatable, and impossible to dismiss. What mattered was not brightness or heat, but orientation. The light carried something that had to be transferred, and the apparatus responded as if it were obeying a familiar conservation law. From that moment, angular momentum stopped being a property reserved for spinning objects and orbiting bodies. It became something light itself could carry, deliver, and hand over to matter. As experiments refined lasers and learned to shape electromagnetic fields, the effect did not disappear. It became more precise. Polarization revealed one contribution, structure revealed another, and across laboratories, the accounting always balanced. Nothing extra appeared. Nothing went missing. And this trail leads first to a basic but stubborn place. Part 1. If light has no mass, what exactly is turning when it carries angular momentum? Nothing touches the object. Nothing pushes it from the side, and yet it begins to rotate. That is the observation that refuses to sit comfortably inside the old picture of light as a straight, harmless ray. A beam passes through space, meets matter, and leaves behind a measurable twist. Not heat, not vibration, rotation. For a long time, physics had no experimental reason to take that idea seriously. Light was already known to carry energy and linear momentum. Radiation pressure had been predicted by James Clerk Maxwell in the 19th century and confirmed soon after. Mirrors recoil, comets grow tails, solar sails become possible. But angular momentum belonged, almost by instinct, to objects with mass wheels, planets, atoms in orbit. Light seemed exempt. That exemption ended quietly in 1936. At Bell Telephone Laboratories, physicist Richard A. Beth designed an experiment that was intentionally narrow in scope. He was not trying to redefine light. He wanted to test a specific consequence of electromagnetic theory, whether circularly polarized light could exert a torque. The prediction existed in Maxwell's equations, but no one had shown it directly. Beth suspended a thin quartz plate using a torsion fiber so sensitive that even a minute angular displacement could be detected. The setup was carefully isolated. Vibrations were minimized. Thermal effects were controlled. Then he sent a beam of circularly polarized light through the plate. The fiber twisted. When the handedness of the polarization was reversed, the direction of rotation reversed as well. When the beam was blocked, the motion stopped. When the experiment was repeated, the result returned. The effect did not depend on brightness alone. It depended on polarization. Beth summarized the outcome without embellishment. The electromagnetic theory of the torque exerted by a beam of polarized light was confirmed by direct measurement. The sentence matters because it does not describe a metaphor. It describes torque, angular momentum transfer, registered by a mechanical system. At that point, angular momentum stopped being a property that light merely borrowed from language. It became something light could carry and exchange. To see why this is unavoidable, it helps to slow down and look at what circular polarization actually means. In linearly polarized light, the electric field oscillates back and forth along a fixed direction. In circular polarization, the electric field rotates as the wave propagates. That rotation is not an animation layered on top of the wave. It is part of the field's structure. Electromagnetic theory assigns angular momentum density to that rotating field. If the field interacts with matter in a way that changes its polarization state, angular momentum must be conserved. There is no loophole. Either the light keeps it, or matter takes it. The torsion balance does not care about interpretation. It responds only to conservation laws. As optical technology improved through the mid-20th century, the Bethe result did not fade into a historical footnote. It became a reference point. Lasers made polarization control precise. Wave plates allowed deliberate flipping between left-handed and right-handed states. Each time the polarization changed, a compensating rotation appeared in the optical element. The angles were small, but they were consistent. What mattered was that the bookkeeping always closed. Nothing extra appeared, nothing vanished. By the 1970s and 80s, this behavior was no longer confined to delicate torsion fibers. Arthur Ashkin and colleagues demonstrated that focused laser beams could trap microscopic particles using radiation pressure and intensity gradients. These optical tweezers allowed forces and torques to be measured at the scale of micrometers. When circularly polarized light was used, trapped particles rotated, changed the polarization, and the rotation followed. Ashkin later wrote, "I have always been fascinated by the forces that light can exert on objects." The fascination was justified. The forces were weak, but they were real, predictable, and tied directly to angular momentum flow in the electromagnetic field. Up to this point, the story might still seem limited to polarization. One could imagine that spin angular momentum belonged to light in the same way handedness belongs to waves. But in the early 1990s, a different contribution came into view, one that had nothing to do with polarization at all. Researchers studying laser beam modes noticed that certain solutions of the paraxial wave equation carried angular momentum even when the polarization was fixed. These were Laguerre-Gaussian modes, characterized by a phase that winds around the beam axis. As you move once around the center, the phase advances by an integer multiple of 2 pi. At the center, the intensity drops to 0, forming a dark core. This phase structure is not cosmetic. It carries orbital angular momentum. Each photon in such a beam carries an integer multiple of the reduced Planck constant, determined by the winding number of the phase. The confirmation, once again, came from matter. Microscopic particles placed in these beams did not simply spin in place. They orbited around the beam axis. The direction depended on the sign of the phase winding. Adjust the spatial light modulator shaping the wavefront, and the orbital motion adjusted with it. Nothing in this behavior could be attributed to heating or random scattering. The angular momentum lived in the geometry of the field. By now, angular momentum of light had split cleanly into 2 contributions: spin, tied to polarization, and orbital, tied to spatial structure. Quantum electrodynamics accommodates both without strain. The field description remains continuous. The photon description introduces quantization. Both predict the same transfer when measurements are performed. Single photon experiments pushed the accounting even further. When photons were sent, one at a time, through polarization-changing elements, the statistics of angular momentum transfer matched theoretical predictions exactly. The torsion balance had measured an average effect decades earlier. The quantum experiments showed that the average emerged from discrete events. Richard Feynman once remarked, "I think I can safely say that nobody understands quantum mechanics." Yet in this corner of it, understanding was not optional. Conservation laws enforced consistency whether one spoke in terms of fields or photons. Beyond the laboratory, the same principles operate on astronomical scales. Sunlight carries momentum and angular momentum into interplanetary space. Dust grains absorb and re-emit radiation asymmetrically, changing their rotation rates over time. NASA has measured these effects in studies of the YORP mechanism. where radiation torque alters the spin of small asteroids. The equations governing those changes are the same ones Beth tested in miniature. Solar sail concepts, studied by both NASA and ESA, rely on momentum transfer from photons, reflecting off large, lightweight surfaces. Engineers must account not only for linear momentum but also for torque when sails are tilted. The light has no mass, yet its momentum shapes trajectories. Across all these contexts, one theme repeats. Light behaves as if it has internal structure. That structure carries conserved quantities. When the structure is altered, matter responds, so the original discomfort returns, sharpened rather than softened. If light has no mass, no surface, and no solidity in the usual sense, then what exactly is turning? The answer is not a hidden wheel or a spinning particle core. The turning belongs to the electromagnetic field itself. Angular momentum is encoded in how the field is arranged in space and time, in polarization, in phase, in symmetry. When light interacts with matter, those arrangements must be accounted for. Matter rotates because the field's structure demands it. Beth's torsion balance remains the cleanest demonstration because it stripped away every distraction. A fiber twisted. The twist followed polarization. Conservation closed the ledger. From that point on, any honest description of light had to include angular momentum as something real. And once angular momentum is accepted as a property of field structure rather than mass, another consequence follows. Describing the shape of light stops being a visual convenience and becomes a physical necessity, one that becomes directly relevant when the field itself is deliberately sculpted in the next part. Part 2. Why does circular polarization behave like a built-in spin? And why can a wave plate feel it? Light can rotate matter even when nothing appears to be rotating. That is the uncomfortable observation at the center of circular polarization. A beam travels straight, its intensity steady, its direction unchanged. Yet when its polarization state is altered, a solid optical element twists in response. No friction is involved. No surface is pushed sideways. The motion appears only when the handedness of the light is changed. Something intrinsic is being exchanged. To understand why this happens, it is necessary to step away from the familiar picture of polarization as a visual orientation and treat it instead as a physical state with consequences. In classical electromagnetism, polarization describes how the electric field vector evolves in time as the wave propagates. Linear polarization oscillates back and forth along a fixed line. Circular polarization does something fundamentally different. The electric field rotates at a constant rate, tracing a circle in the plane perpendicular to the direction of travel. That rotation is synchronized with the wave's frequency. It is not added afterward. It is built into the solution of Maxwell's equations. When James Clerk Maxwell unified electricity and magnetism in the 19th century, he showed that electromagnetic waves carry energy and momentum. What was not obvious at the time was that they also carry angular momentum when their fields possess rotational structure. Circular polarization is the simplest example of such structure. The field itself rotates, and with that rotation comes a conserved quantity. For decades, this idea remained largely theoretical. Polarization was treated as a convenient descriptor for optics, rather than a carrier of mechanical consequences. That changed gradually as experimental techniques improved. The torsion balance experiments of the early 20th century showed that polarized light could exert torque. Later work refined the picture and made the bookkeeping unavoidable. A key tool in this story is the wave plate. A wave plate is a slab of birefringent material, meaning it has two refractive indices, depending on the orientation of the electric field. Light entering the plate splits into two components that travel at different speeds. When they recombine upon exiting, the polarization state has changed. A quarter-wave plate can convert linear polarization into circular polarization, or reverse the handedness of circular polarization entirely. This conversion is not passive. When a wave plate flips left-handed circular polarization into right-handed, the angular momentum carried by the light changes sign. Conservation laws demand compensation. The wave plate must absorb the difference. The result is a tiny but measurable torque acting on the plate. This is not a matter of interpretation. It is measured. Experiments using suspended wave plates and sensitive torsion fibers show that the plate rotates when the polarization is flipped, and that the direction of rotation follows the handedness change precisely. When the input polarization is unchanged, the plate remains still. When the beam is blocked, the motion stops. The response tracks angular momentum transfer alone. At the photon level, the accounting becomes even clearer. Circularly polarized light carries spin angular momentum. Each photon contributes 1 unit of reduced Planck constant, with the sign determined by handedness. This is not inferred from analogy. It is derived from quantum electrodynamics and confirmed through interaction statistics. When photons pass through a device that changes their polarization state, the angular momentum difference must be transferred to matter, photon by photon. This is where circular polarization reveals itself as more than a visual property. It behaves like built-in spin, because, in a precise physical sense, it is. The spin is not attached to a tiny rotating object inside the photon. It arises from the symmetry of the electromagnetic field. Rotation in the field corresponds to angular momentum in the conservation ledger. One way to see this without equations is to think in terms of cause and effect. If circular polarization were merely a descriptive label, changing it would have no mechanical consequence. The wave plate would feel nothing. But the plate does rotate. That rotation is the effect. The cause must be a conserved quantity being transferred. The only candidate consistent with all observations is spin angular momentum carried by the light. Laboratories around the world reproduced these results throughout the second half of the 20th century. Improved lasers allowed cleaner polarization states. Better isolation reduced noise. The measured torques matched theoretical predictions with increasing precision. Nothing in the results depended on subjective interpretation. The balance always closed. Arthur Ashkin's work with optical tweezers added another layer of clarity. By trapping microscopic particles in focused laser beams, his experiments made radiation pressure and torque visible at the scale of individual objects. When circularly polarized light was used, trapped particles rotated steadily. When the handedness was reversed, the rotation reversed. The angular speed depended on the photon flux, not on heating or chemical effects. Ashkin later reflected on this body of work by saying, "I have always been fascinated by the forces that light can exert on objects." The fascination was grounded in reproducibility. The forces were weak, but they obeyed the same conservation laws as any mechanical system. Quantum electrodynamics provides the framework that unites these observations. In that theory, the electromagnetic field is quantized into photons, but the field retains its structure. Spin angular momentum emerges naturally from the field's rotational symmetry. There is no need to imagine internal gears or hidden motion. The spin is intrinsic because it is inseparable from the field configuration itself. This intrinsic nature becomes especially clear when comparing circular polarization to linear polarization. Linear polarization carries no net spin angular momentum. Passing linearly polarized light through a wave plate that merely rotates the polarization direction produces no torque. The plate feels nothing because no angular momentum balance is altered. Only when the polarization state includes rotation does angular momentum enter the exchange. These principles extend beyond the laboratory. NASA and ESA missions account for photon momentum and angular momentum when modeling spacecraft behavior. Solar radiation does not merely push, it can twist. Small torques accumulate over long timescales, influencing the orientation of spacecraft surfaces and the spin states of dust grains in space. Astrophysical observations show the same physics at work. Interstellar dust grains align under the influence of radiation fields, a process that depends on angular momentum transfer from light. Polarization measurements of starlight rely on this alignment to infer magnetic field structures across the galaxy. The interpretation rests on the fact that polarized light can exchange angular momentum with matter. What makes circular polarization particularly revealing is its simplicity. There is no complex spatial structure required, no twisted wavefronts, no elaborate beam shaping. A uniform plane wave, if circularly polarized, carries spin angular momentum. The effect is present even in the most basic solutions of Maxwell's equations. That simplicity is why circular polarization became the testing ground for understanding light's spin. Once its mechanical effects were confirmed, more complex forms of angular momentum could be explored with confidence. The waveplate did not just convert polarization, it converted abstract theory into physical response. Carl Sagan often emphasized that science advances when hidden connections are revealed through careful measurement rather than dramatic claims. He once wrote, "Science is a way of thinking, much more than it is a body of knowledge." In the case of circular polarization, the way of thinking required abandoning the idea that light's properties end at appearance. The story behind these discoveries is not one of sudden revelation, but of persistence. Experimentalists refined torsion balances to eliminate thermal drift. Optical engineers developed birefringent materials with precise retardation. Quantum theorists worked out how field symmetries translate into measurable quantities. Each step reduced ambiguity. By the time single-photon experiments became routine, the conclusion was unavoidable. Spin angular momentum is intrinsic to light. It does not emerge from interaction alone. It is carried from the moment the field exists, in a circularly polarized state. Matter responds because conservation demands it. The waveplate feels the spin because it must. If it did not, angular momentum would be lost or created without cause. Every successful measurement confirms the same rule, and yet, this clarity opens a wider door. If polarization can encode intrinsic spin, and if matter can register it mechanically, then angular momentum is not confined to polarization alone. The structure of the field itself becomes a variable that can carry and exchange rotation. At that point, the distinction between a new form of angular momentum and a new configuration of the field appears. Part 3. When a beam twists, is that a new kind of angular momentum or a new shape of the field? A beam of light can make matter orbit, even when nothing in the beam appears to be rotating at all. That single observation overturned a quiet assumption that had survived for decades. The idea that angular momentum in light must always be tied to polarization alone. In laboratories where polarization was carefully held fixed, particles still began to circle an invisible axis, tracing paths that could not be explained by spin. Something else was present, embedded not in how the field oscillated, but in how it was arranged across space. To see why this mattered, it helps to recall where the story stood before this point. Spin angular momentum had already earned its place. Circular polarization rotated matter because the electric field itself rotated in time. That picture was coherent, testable, and complete. But then came experiments where polarization was deliberately neutralized, set to linear, stripped of any built-in rotation. The light should have lost its ability to twist. It did not. The turning showed up anyway. What changed was not the polarization, but the shape of the wavefront. Instead of flat planes marching forward, the phase of the light wound around its own axis. As you moved in a circle around the beam center, the phase advanced steadily, completing full turns before returning to its starting point. At the center, the intensity fell to zero, forming a dark core. The beam no longer resembled a simple column of light. It had structure. This was not noticed by accident. In the late 1980s and early 1990s, laser physicists were cataloging solutions to the paraxial wave equation, the mathematical description of how laser beams propagate when they are narrow and well collimated. Among these solutions were modes known as Laguerre-Gaussian beams. They had been written down before, but their physical consequences were not fully appreciated. In 1992, Les Allen and his colleagues published a paper that reframed the entire discussion. They showed that these beams carry a distinct form of angular momentum that depends on the winding of the phase, not on polarization. Each photon in such a beam carries an amount of angular momentum proportional to that winding number. The quantity was not small. It could be several times larger than the spin carried by circular polarization. The claim was unsettling for a simple reason. If true, angular momentum in light was no longer limited to how the field rotated in time. It could also reside in how the field was organized across space. The distinction mattered. Spin had seemed intrinsic. This new contribution depended on geometry. Once again, the decisive tests came from matter. Microscopic particles placed in these beams did not simply spin in place, as they did under circular polarization. They moved around the beam axis, following circular paths, whose radius and direction depended on the phase structure of the light. When the sign of the phase winding was reversed, the direction of motion reversed. When the winding number increased, the orbital motion strengthened. The response tracked the beam's structure with precision. There was no need to invoke exotic explanations. Conservation laws did the work. The light carried angular momentum. Matter absorbed it. The balance closed. The language that emerged was orbital angular momentum, abbreviated OAM, to distinguish it from spin. The term was chosen carefully. This was not rotation of the electric field vector itself. It was angular momentum associated with the spatial distribution of the field. The beam behaved as if its energy flowed along helical paths, wrapping around the propagation axis as it moved forward. Importantly, this effect did not require high power. Even weak beams produced measurable orbital motion if the phase structure was clean. The phenomenon depended on coherence and geometry, not brute force. That made it attractive for precision experiments and, eventually, for applications. The story behind its acceptance was gradual. Early skepticism focused on interpretation. Was this truly a new form of angular momentum, or merely a rearrangement of linear momentum components? Experiments answered that question the same way they had before, by letting matter respond. The torques and forces matched predictions that treated OAM as a conserved quantity distinct from spin. Quantum theory accommodated the result without strain. In quantum electrodynamics, photons are excitations of the electromagnetic field. The field can be decomposed into modes, and those modes carry well-defined conserved quantities. Laguerre-Gaussian modes carry orbital angular momentum because their phase structure breaks rotational symmetry in a specific way. The mathematics was precise, but the physical meaning was simpler. Shape matters. This insight changed how laser modes were understood. Modes were no longer just patterns of brightness. They were carriers of physical properties that could be transferred, measured, and exploited. Optical elements that shaped wavefronts, such as spiral phase plates and later spatial light modulators, became tools for engineering angular momentum directly. Once these tools existed, the catalog of experiments expanded quickly. Optical tweezers were revisited with structured light. Trapped particles could be made to orbit controllably. Biological samples could be rotated without mechanical contact. The torque could be tuned by adjusting the phase pattern alone. The polarization remained unchanged. Astronomy provided a parallel perspective. Although telescopes do not typically generate OAM deliberately, The propagation of light through turbulent media can scramble phase structure. Studies of atmospheric turbulence showed how OAM modes degrade over distance, a fact that later became crucial for communication experiments. The sensitivity of OAM to phase distortion was not a flaw, it was a diagnostic. By the early 2000s, researchers began exploring OAM as a resource for information transfer. Unlike polarization, which offers two basic states, OAM provides a potentially unbounded set of modes. Each winding number represents a distinct channel. In principle, this allows multiple data streams to share the same frequency and polarization. Practical limits appeared quickly. Atmospheric turbulence mixes modes. Imperfect optics reduce purity. Detectors struggle to discriminate cleanly, yet the underlying physics remained sound. OAM was real, conserved, and transferable. Its fragility was a property of wave propagation, not a failure of theory. Space agencies took note, not because of communication fantasies, but because structured light sharpened understanding of wave propagation itself. NASA and ESA missions depend on precise models of how electromagnetic fields behave over long distances. Phase structure, coherence, and angular momentum all influence measurements, from interferometry to optical navigation. Even when OAM is not used intentionally, its principles inform how beams evolve. What made the discovery of OAM especially significant was how little it relied on intuition. Nothing in everyday experience suggests that a beam can twist without spinning internally. The effect only becomes obvious when geometry is allowed to carry physical weight. The phase, invisible to the eye, becomes decisive. Carl Sagan once observed that science advances when we learn to read nature's subtler signals rather than insisting on familiar pictures. He wrote, "Somewhere, something incredible is waiting to be known." In this case, the incredible was not hidden in distant galaxies, but in the cross-section of a laser beam on a laboratory table. The engineers and physicists who recognized OAM did not set out to overturn intuition. They followed the mathematics, tested it against matter, and let the results stand. The beam twisted because its structure required it. No additional assumptions were needed. By now, a pattern had formed across all three parts of this story. First, light was shown to push. Then, it was shown to spin. Now, it was shown to orbit. Each step relied on conservation laws and careful measurement. Each step revealed that properties once assigned exclusively to massive objects also belong to fields when their structure allows it. This does not mean that light behaves like matter. It means that fields can store and transport quantities traditionally associated with motion. The difference lies not in the laws, but in the medium. As researchers became comfortable with OAM, attention shifted toward control. If angular momentum could be encoded in phase, then wavefront shaping became a form of mechanical engineering conducted with light. The field itself became the object to be designed. Once orbital angular momentum is traced to phase structure, its presence depends entirely on how that structure is organized. When phase structure is deliberately engineered, twisted modes remain stable and detectable. In common light sources, such as flashlights or sunlight, the same rotational components fail to persist, not because angular momentum is absent, but because the field lacks the coherence required to sustain ordered structure. Part 4. If orbital angular momentum is real, why doesn't it show up in everyday flashlights? If twisted light can carry angular momentum through empty space, then its absence in ordinary illumination is not a mystery of weakness, but of preparation. A flashlight fills a room with photons by the trillions, yet none of them arrive with a coordinated twist. The difference is not power, it is order. To see why orbital angular momentum does not appear in everyday light sources, it helps to return to what OAM actually depends on. Spin angular momentum is tied to polarization, a property that can survive even in messy conditions. Orbital angular momentum is different. It lives in the geometry of the electromagnetic field itself, encoded in how the phase of the wave changes across space. That geometry is fragile. It must be built deliberately. A common flashlight emits light from a filament or LED, where countless microscopic emitters radiate independently. Each emitter produces waves with random phase relationships. As the waves spread and overlap, any large-scale phase structure is washed out. The result is brightness without coherence. Angular momentum associated with spatial structure cannot survive that kind of disorder. Lasers changed this landscape by introducing coherence. In a laser cavity, photons stimulate the emission of other photons with the same phase, frequency, and direction. The beam that emerges is not just bright, it is organized. That organization makes wavefront shaping possible. Even so, a bare laser does not automatically carry orbital angular momentum. Most lasers emit beams whose phase fronts are flat or gently curved. To create OAM, those wavefronts must be sculpted. This is where optical engineering enters the story. One of the earliest tools developed for this purpose was the spiral phase plate. This optical element has a thickness that increases smoothly with angle around its center. As light passes through, different parts of the wave are delayed by different amounts. By the time the beam exits, its phase has wrapped around the axis in a controlled way. The result is a vortex beam, marked by a dark core and a helical phase. Later, spatial light modulators made this process far more flexible. These devices use electronically controlled pixels to impose precise phase shifts across a beam. By programming the phase pattern, researchers can generate beams with chosen orbital angular momentum values, switch between them rapidly, or superpose multiple modes. The twist is not imposed by force. It is written into the field. Detecting OAM requires equally careful preparation. Brightness alone is not a signature. The most telling features are geometric. Interference patterns reveal forked fringes where phase singularities exist. When a vortex beam interferes with a reference beam, the number of fringe dislocations corresponds directly to the winding number of the phase. These patterns are not artistic flourishes, they are measurements. Matter provides confirmation as well. Microscopic particles placed in vortex beams orbit the beam axis. The direction and speed depend on the engineered phase structure. Remove the phase winding, and the orbital motion disappears. The particles respond to geometry, not to polarization. This distinction explains why OAM does not appear in sunlight or lamplight in any controlled way. The sun emits light from a turbulent plasma surface. The phases are uncorrelated across large distances. By the time sunlight reaches Earth, any structured phase information has long been scrambled. The same is true for incandescent bulbs and LEDs. In astronomy, this scrambling is familiar. Atmospheric turbulence distorts wavefronts from distant stars, blurring images. Adaptive optic systems, developed and refined by observatories working with agencies such as NASA and ESA, correct these distortions in real time. The goal is not to create OAM, but to remove unwanted phase structure. The techniques reveal just how sensitive spatial phase really is. The sensitivity of OAM to disturbance once led some researchers to question its physical relevance. If it disappears so easily, could it really be fundamental? Experiments answered that concern. The angular momentum does not vanish. It redistributes. Turbulence mixes modes, spreading angular momentum across many channels rather than erasing it. Conservation still holds. This understanding reframed the problem. OAM is not absent in everyday light because it is unreal. It is absent because everyday sources do not impose the coherence and symmetry required to make it visible. Structure is not free. It must be engineered. The history of vortex beams reflects this gradual realization. Early reports of phase singularities were treated as mathematical curiosities. Only when experimentalists learned to isolate and measure their effects did the physical picture settle. By the late 1990s, vortex beams had become standard tools in optics laboratories. The twist was no longer surprising. It was controllable. Applications followed naturally. Optical tweezers using vortex beams allowed particles to be rotated around chosen axes without contact. Microfluidic systems used light-driven rotation to stir fluids at small scales. In each case, the requirement was the same. The wavefront had to be prepared with care. Communications researchers saw another opportunity. If different OAM modes are orthogonal, they can carry independent data streams. Experiments demonstrated multiplexing using multiple orbital angular momentum channels on the same frequency. The promise was large. The limitations were immediate. Atmospheric turbulence and optical imperfections degrade mode purity. The physics remained sound. The engineering challenge was formidable. Space agencies monitored these developments closely. Long-distance optical links, whether between satellites or between spacecraft and Earth, depend on precise control of beam structure. Understanding how phase geometry evolves during propagation is essential, even when OAM is not the goal. Structured light-sharpened models of beam spreading, distortion, and correction. What becomes clear through all of this is that orbital angular momentum belongs to the field, not to the source. A flashlight cannot produce OAM because it does not control phase across its aperture. A laser equipped with wavefront shaping can, even at low power. The difference lies entirely in geometry. This also clarifies a common misunderstanding. OAM is not hidden spin. It does not reside in polarization. A beam can be linearly polarized and still carry large orbital angular momentum. Conversely, a circularly polarized beam can carry spin without any orbital contribution. The two forms are independent, additive, and conserved separately. The absence of OAM in everyday light is therefore not a failure of nature to display an exotic property. It is a reminder that nature does not organize phase for convenience. Organization must be imposed. When it is, the consequences are immediate and measurable. Carl Sagan often emphasized that phenomena which seem exotic are often absent from daily experience, not because they are rare, but because the conditions that reveal them are uncommon. He wrote, "Nature is always more subtle, more intricate, more elegant than what we are able to imagine." Orbital angular momentum fits that pattern. It is present whenever symmetry and coherence allow it to emerge. By understanding why flashlights do not twist matter into orbit, we gain a clearer view of what structured light actually is. It is not stronger light. It is not stranger light. It is light whose internal geometry has been prepared with intention. The twist carried by structured light does not remain confined to rotation within the beam. As angular momentum propagates through space, it can cross boundaries and enter material systems, where its flow produces measurable forces and displacements. At that scale, momentum is no longer an abstract quantity transported by the field alone, but something that can be exchanged directly between light and matter. Part 5. Can light grab matter? Like invisible fingers, and what does that reveal about momentum flow? A beam of light can hold a solid particle in place against gravity. That fact alone is enough to unsettle the familiar boundary between what touches and what does not. No glue, no container, no mechanical support, only photons, arriving, scattering, and leaving behind a steady force that balances weight and motion. Once this is accepted, the next step follows without ceremony. If light can push and hold, then it can also twist. The question is not whether this happens, but how momentum flows through the field to make it unavoidable. The path toward that understanding runs through the work of Arthur Ashkin. In the late 1960s, Ashkin was studying radiation pressure, the transfer of linear momentum from light to matter. Maxwell's equations had predicted it long before, and experiments had confirmed that photons, reflecting from a surface, impart a small but measurable force. What Ashkin noticed was that under the right conditions, that force could be shaped. By tightly focusing a laser beam, he created a region where the intensity changed rapidly with position. Microscopic particles, placed near the focus, experienced a restoring force, pulling them toward the region of highest intensity. The particle was not pushed away, it was drawn inward and held there. Optical trapping was born. Ashkin later described his motivation plainly. "I have always been fascinated by the forces that light can exert on objects." The fascination deepened as the experiments progressed. Trapped particles could be moved by steering the beam. They could be held for long periods. Forces on the order of piconewtons could be applied and measured, small but precise. What made optical tweezers decisive for this story was not just trapping, but control. Once a particle is held in a beam, any momentum carried by the light must go somewhere. Linear momentum produces force. Angular momentum produces torque. The same bookkeeping governs both. When circularly polarized light was used in optical traps, trapped particles began to rotate. The direction followed the handedness of polarization, reversed the handedness, and the rotation reversed. The particle was not being heated into motion. Its rotation rate depended on photon flux and polarization state, not on temperature rise. This behavior made angular momentum flow visible at the scale of micrometers. The field carried spin angular momentum. The particle absorbed it. Conservation demanded rotation. Orbital angular momentum added another layer. When vortex beams were used in optical traps, particles did not merely spin in place. They moved around the beam axis, tracing circular paths. The radius and speed of these orbits depended on the engineered phase structure of the beam. Change the structure, and the motion followed. In these experiments, the phrase momentum flow becomes concrete. Momentum is not an abstract label attached to light. It is something that arrives continuously, carried by the electromagnetic field, redistributed through scattering and absorption, and converted into mechanical motion. Optical tweezers act as a translator between field properties and material response. The forces involved are small, but their predictability is what matters. A particle of known size and refractive index placed in a beam of known intensity experiences forces that can be calculated and then measured. The agreement between prediction and observation tightened over decades of refinement. Nothing mystical was left behind. Biophysics quickly adopted these tools. Optical tweezers allowed researchers to pull on DNA strands, measure the stiffness of molecular motors, and probe cellular mechanics without physical contact. In these contexts, momentum flow from light became a practical instrument. Forces measured in piconewtons revealed processes invisible to conventional tools. Angular momentum played a role here as well. Rotational control enabled the twisting of biological structures, the study of torque generation in enzymes, and the manipulation of anisotropic particles. The same conservation laws applied whether the object was a glass bead or a protein complex. Beyond the laboratory bench, the same principles appear in space science. NASA missions have long accounted for radiation pressure in spacecraft design. Solar photons striking a surface impart momentum. Over time, this force alters trajectories and orientations. When surfaces are angled, torque appears. Spacecraft attitude control systems must account for it. The Europe effect, observed in small asteroids, provides a natural example. As sunlight is absorbed and re-emitted asymmetrically, angular momentum is transferred. The asteroid's rotation rate changes measurably over years. Observations confirm the predictions. Light reshapes motion, even on astronomical scales. These phenomena all point back to the same underlying structure. Momentum in light is carried by the electromagnetic field. When the field interacts with matter, momentum flows according to geometry, intensity, and phase. Optical tweezers simply isolate the interaction so that it can be seen clearly. What is striking is how little is required to make light grab matter. No exotic materials, no extreme energies, only coherence and focus. The field's gradients do the work. A particle finds itself in a landscape shaped by light, and the conservation laws guide its motion. The term invisible fingers is tempting but misleading. Light does not grasp, it exchanges momentum. The grip is an accounting result, not a mechanism layered on top. The particle stays where forces balance, just as any object does in a mechanical trap. This clarity was hard-won. Early skepticism centered on whether optical trapping violated intuitive ideas about force. It did not. It expanded them. Momentum does not require mass in the way intuition suggests. Photons carry it by virtue of their energy and propagation. The field distributes it according to its structure. Carl Sagan often reminded his audience that understanding grows when intuition yields to measurement. He wrote, "The universe is not required to be in perfect harmony with human ambition. In optical trapping, ambition followed measurement. The behavior of light dictated the design of experiments, not the other way around." As techniques matured, researchers learned to shape momentum flow with increasing precision. Multiple traps could be created from a single beam. Angular momentum could be tuned independently of linear force. Structured light allowed forces and torques to be combined in controlled ways. The field became a toolkit. At every stage, conservation laws held firm. When a particle spun faster, angular momentum in the outgoing light decreased accordingly. When force increased, momentum flux increased. Measurements closed the loop. What optical tweezers ultimately revealed is that momentum flow in light is not a theoretical convenience. It is a physical process that can be directed, partitioned, and measured. The same photons that push a solar sail can rotate a bead in water. Scale changes, laws do not. This brings the story to a subtle boundary. If momentum flow can be shaped to hold, push, and spin matter, then the description of light must include more than energy and direction. It must include how momentum is distributed across the field. That distribution carries information about intensity, polarization, and structure. As light is treated as a carrier of structured momentum rather than a uniform flow of energy, its internal properties begin to separate in measurement. Momentum transfer depends not only on intensity, but on how phase is arranged and how the field is prepared at the quantum level. In that context, the physical meaning of the shape of light becomes tied to which aspects of the field remain accessible to observation and control. Part 6. What does the shape of light mean in physics: intensity, phase, or the quantum state? Two beams of light can look identical to the eye and yet behave as completely different physical objects when they interact with matter. That fact unsettles one of the most persistent habits in optics, the instinct to equate appearance with structure. A camera records brightness. A screen shows a glowing profile. But angular momentum, torque, and momentum flow respond to features that may never appear in an image. The word shape turns out to hide several meanings, and physics must choose carefully which one matters. In everyday experience, the shape of a light beam seems obvious. It is the bright spot on a wall, the circular disc from a laser pointer, the soft spread from a lamp. This is the intensity profile, the distribution of energy across space. It is easy to photograph, easy to describe, and often misleading. Intensity alone does not determine how light exchanges momentum. Two beams with the same brightness pattern can produce different forces and torques. Optical tweezers demonstrated this clearly. A trapped particle responds not just to how much light arrives, but to how that light is organized. The visible shape is only the first layer. Beneath intensity lies phase. Phase describes where the wave is in its oscillation at each point in space and time. Unlike intensity, phase is invisible to direct observation, yet it governs interference, diffraction, and the flow of energy and momentum. In the previous parts, orbital angular momentum emerged entirely from phase structure. The brightness profile alone could not reveal it. This distinction was not always appreciated. Early optics treated beams largely in terms of rays and intensities. Phase entered calculations but rarely intuition. That changed as interferometry matured. When beams were combined, small phase differences produced large observable effects. The invisible became decisive. The recognition that phase carries physical weight transformed optics into a science of structure rather than appearance. Laguerre Gaussian beams offered a clear example. Their intensity profile shows a ring with a dark center, but that darkness is not the defining feature. It is a consequence of a phase singularity, a point where phase is undefined because it winds continuously around the axis. The angular momentum lives in the winding, not in the ring. Experiments confirmed this repeatedly. Particles orbit in vortex beams because of phase gradients. Remove the phase structure while keeping the intensity similar, and the orbital motion disappears. The beam still looks like a ring. It no longer behaves like one. This led to a more careful use of language. When physicists speak of the shape of light, they must specify which layer they mean. The beam profile describes intensity. The phase structure describes how the wavefront is arranged. Both are properties of the electromagnetic field. But there is a third layer that becomes unavoidable at low light levels and precise measurements. That layer is the quantum state. In quantum optics, light is described in terms of modes. A mode is not just a pattern of brightness or phase. It is a complete specification of how the field behaves, including its spatial structure, frequency, polarization, and phase relationships. Photons occupy modes. Angular momentum is associated with particular modes, not with isolated points in space. Mode decomposition became an essential tool. Any beam can be expressed as a combination of modes, each carrying well-defined properties. In this language, orbital angular momentum appears as a property of specific mode families. A measurement that resolves modes reveals angular momentum directly. A measurement that averages over modes hides it. This distinction matters for experiments. Consider a detector that measures total intensity without resolving phase. It cannot distinguish between different OAM states. The angular momentum flows through unnoticed. Introduce an interferometric element, or a mode sorter, and the same beam reveals its structure immediately. The history of this realization is tied closely to advances in instrumentation. Spatial light modulators allowed precise control over phase. Mode sorters, based on refractive and diffractive optics, mapped different OAM states to different positions on a detector. These devices did not create new physics. They made existing physics visible. NASA and ESA have relied on similar principles in astronomical interferometry. Telescopes such as those involved in space-based interferometric missions combine light from separate apertures. Phase information must be preserved and measured with extreme precision. The resulting data depend not on intensity alone, but on phase coherence across large distances. Even when JWST images distant galaxies, phase plays a hidden role. The segmented mirror design requires precise phase alignment between segments to produce sharp images. The brightness distribution on the detector is the final product. The underlying success depends on controlling phase to fractions of a wavelength. This brings clarity to the question of which shape matters when discussing angular momentum. Intensity shape tells us where energy is. Phase shape tells us how that energy moves and circulates. The quantum state tells us how these features are packaged into discrete, conserved units. All three are real. They answer different questions. Angular momentum responds primarily to phase and mode structure. Spin depends on polarization, which is itself a property of the field's temporal structure. Orbital angular momentum depends on spatial phase. Neither can be inferred reliably from intensity alone. This explains why naive pictures often fail. There is a practical lesson here. In experiments claiming to generate or detect structured light, verifying intensity profiles is insufficient. Researchers must demonstrate phase control or mode purity. Otherwise, apparent structure may not correspond to conserved quantities. This rigor is why the field matured slowly and carefully. Carl Sagan often spoke about the importance of careful definitions in science. He noted that confusion often arises not from lack of data, but from imprecise language. He wrote, "If you wish to make an apple pie from scratch, you must first invent the universe." In optics, if one wishes to talk about the shape of light, one must first specify which universe of description is being used. The story behind mode language reflects this need. Early laser physics focused on cavity modes as mathematical conveniences. Over time, experiments showed that modes carry physical meaning. Switching modes altered force, torque, and information capacity. The abstraction gained substance. Quantum optics sharpened the point further. In single-photon experiments, intensity becomes probabilistic. Phase relations persist. The quantum state captures both. A single photon prepared in a superposition of OAM modes can produce interference effects that reveal angular momentum structure without ever showing a classical beam profile. This does not mean that classical pictures are wrong. They are incomplete. Classical fields and quantum states converge in their predictions for measurable quantities. The difference lies in description, not outcome. Conservation laws bridge the two. Understanding which shape matters also resolves apparent contradictions. Why can two beams with identical brightness profiles exert different torques? Because their phase structures differ. Why can angular momentum be present without visible rotation? Because the rotation is encoded in phase, not in motion you can see. As optical engineering advanced, researchers learned to treat phase as a design parameter. Wavefront shaping became a way to sculpt momentum flow. This approach underlies modern applications, from optical manipulation to communication systems. The beam is no longer a simple carrier of energy. It is a structured field, yet there are limits. Phase coherence is fragile. Turbulence, scattering, and imperfect optics degrade structure. Mode mixing occurs. Angular momentum spreads across channels. Measurements reflect this redistribution. Nothing violates conservation. The bookkeeping simply becomes more complex. This complexity is not a flaw. It is a feature. It reveals how deeply structure and measurement are intertwined. What one observes depends on what one resolves. Intensity detectors see energy. Interferometers see phase. Mode sorters see quantum structure. So when physics asks about the shape of light, it is not choosing between competing pictures. It is layering them. Each layer becomes relevant when a particular interaction or measurement is considered. Angular momentum lives comfortably across all of them, but it announces itself most clearly where phase and mode structure are resolved. This perspective sets a clear direction for what follows. If shape is not a single property but a hierarchy, then understanding light requires choosing the right level for the question at hand. When angular momentum is involved, geometry and quantum state take precedence over appearance. When light is reduced to the level of individual photons, angular momentum does not dissolve into a continuous background. Discrete detection events still register well-defined transfers of rotational momentum, independent of overall brightness. At that scale, the connection between field descriptions and quantized exchange becomes explicit without relying on classical intensity as a reference. Part 7. If you send one photon at a time, does angular momentum still come in chunks? A single photon can make a detector rotate, even when no second photon is anywhere nearby. That statement presses directly against the comfortable picture built in earlier parts, where angular momentum seemed to flow smoothly through a rotating electromagnetic field. If the field can be diluted until only one quantum remains, and the effect persists, then something discrete is at work beneath the smooth appearance. The question is not whether angular momentum survives at that scale, but how it does so without breaking the field description that has worked so reliably. The idea that light comes in packets was already unsettling when it first appeared. At the beginning of the 20th century, experiments on blackbody radiation and the photoelectric effect forced physicists to accept that energy exchange in light is quantized. Photons entered the language reluctantly, as bookkeeping devices rather than objects with full physical identity. Momentum followed naturally. If a photon carries energy, it must also carry momentum. Angular momentum was slower to fall into line. In classical electromagnetism, angular momentum is distributed continuously throughout the field. It depends on polarization, phase structure, and spatial gradients. Nothing in that picture suggests discreteness. And yet, when light interacts with atoms, molecules, or carefully isolated mechanical systems, the transfer occurs in fixed units. The earliest clues came from atomic physics. Spectroscopy revealed strict selection rules. Atoms absorb or emit light only if angular momentum is conserved exactly. Transitions between atomic states require photons with specific angular momentum values. These rules were not arbitrary. They were measured repeatedly and held across different elements and environments. Circularly polarized light interacts with atoms as if each photon carries a definite spin. Left-handed and right-handed polarization lead to different transition probabilities. No averaging is needed. The interaction is quantized from the start. This was one of the first signs that spin angular momentum is intrinsic at the photon level. As experimental control improved, researchers began to push further. Could angular momentum transfer be observed when photons arrive one by one, separated in time so that no classical field builds up? Single photon sources made this possible. These devices emit photons with well-defined properties at controllable rates, sometimes seconds apart. In such experiments, the smooth field description breaks down as a literal picture. There is no continuous wave carrying momentum. There is only a probability amplitude describing where and how the photon might interact. Yet when the interaction occurs, angular momentum is transferred in a definite amount. Consider a wave plate suspended on a fine fiber, designed to respond to torque. When a stream of photons passes through at high rate, the plate rotates smoothly, matching classical predictions. When the photon rate is reduced so that only one photon interacts at a time, the average rotation remains the same over long periods. The difference lies in how the motion accumulates. Instead of a continuous push, the plate receives a sequence of tiny, discrete kicks. Each kick corresponds to the angular momentum carried by a single photon. Over time, the kicks add up to the same macroscopic rotation predicted by the field description. Nothing contradicts conservation. The smooth picture emerges from many discrete events. This is the pattern that repeats throughout quantum optics. The field description predicts average behavior. The photon description accounts for individual exchanges. Both are correct. They describe different levels of resolution. Orbital angular momentum follows the same rule. When light prepared in a single OAM mode interacts with matter, each photon carries a quantized amount of orbital angular momentum determined by the mode structure. Single photon interference experiments confirm this. Photons prepared in superpositions of OAM modes produce interference patterns that reflect discrete angular momentum values. Detectors sensitive to angular momentum do not record half units or smeared values. They register outcomes consistent with quantization. Over many events, the statistics reproduce the classical torque and force expected from the structured field. This dual description unsettled even the architects of quantum theory. Richard Feynman captured the tension succinctly when he said, "I think I can safely say that nobody understands quantum mechanics." The statement was not a confession of ignorance, but an acknowledgement that intuition built from everyday experience fails at this scale. What matters for this story is that angular momentum does not escape quantization simply because the field looks smooth. The smoothness is an average. The underlying exchanges are discrete. The two views are consistent because conservation laws operate at every scale. NASA and ESA experiments relying on photon detection illustrate this consistency daily. Instruments measuring faint astronomical signals count individual photons arriving from distant sources. Each detection event transfers energy and momentum. Over time, the aggregate produces forces, heating, and measurable pressure. The quantized events reconstruct classical behavior. In optical communication experiments, single photons prepared in specific polarization or OAM states carry information reliably. The angular momentum encoded in each photon is preserved during transmission unless disturbed by scattering or decoherence. Measurements confirm that the information arrives in discrete units, not as partial fragments. The smooth, rotating field picture remains indispensable because it predicts how probability amplitudes evolve. It tells us where photons are likely to go and how their angular momentum is distributed statistically. But when an interaction occurs, nature chooses a definite outcome. The detector turns, or it does not. The atom transitions, or it does not. This does not require invoking paradox. It requires clarity about what is being described. The field is a tool for predicting averages. The photon is the unit of exchange. Angular momentum belongs to both descriptions, expressed differently. Historically, resistance to this view often came from treating photons as miniature particles with trajectories. That picture fails quickly. Photons do not orbit or spin in space like tiny objects. Their angular momentum arises from the symmetry of the field modes they occupy. Quantization reflects the allowed modes, not hidden motion. Experiments with interferometers make this clear. A single photon passing through an interferometer can interfere with itself, producing phase-dependent outcomes. When OAM is involved, the interference patterns depend on discrete mode indices. The photon behaves as a field during propagation and as a quantum during detection. The same logic explains why angular momentum appears in chunks without destroying the field description. The field governs evolution. The quantum governs exchange. The consistency between the two is enforced by conservation laws built into both frameworks. One practical consequence is that angular momentum noise behaves differently from classical noise. In low-light conditions, fluctuations reflect the discrete nature of photons. Shot noise emerges. The variance in torque or force measurements scales with photon number, not with field smoothness. Experiments confirm this scaling precisely. This has implications for precision measurement. Optical torque sensors operating at low photon flux must account for quantization. Averaging restores smooth behavior, but individual events remain discrete. Understanding this allows engineers to design experiments that approach fundamental limits. Carl Sagan often emphasized that scientific understanding deepens when we learn to hold multiple descriptions without forcing them into a single picture. He wrote, "It is far better to grasp the universe as it really is than to persist in delusion, however satisfying and reassuring." In quantum optics, reassurance is rare, but consistency is firm. The one-photon regime does not undermine the reality of angular momentum in light. It confirms it. Each photon carries a definite amount, delivered in a single exchange. The rotating field picture survives because it predicts the statistics of those exchanges accurately. As photon sources became more controllable, experiments demonstrated this unity repeatedly. Single photons trapped atoms, transferred torque, and encoded information. The results matched both quantum and classical predictions in their respective domains. The boundary between smooth and discrete shifted depending on how closely one looked. This leaves the story at a productive tension. Angular momentum is both continuous in description and discrete in transfer. Neither view replaces the other. Each becomes necessary under different conditions. When angular momentum remains well-defined at the level of individual photons, the modes of the field begin to matter as much as its intensity. Structured light can encode distinct states through its spatial and phase organization, allowing information to be carried alongside momentum in each photon. At that scale, twisted modes are no longer just optical patterns, but channels through which information can be encoded, transmitted, and preserved. Part 8. Is twisted light just optics, or does it carry more information per photon? A single photon can be identical in energy, color, and arrival time to another, and still represent a completely different message. That statement challenges the most basic intuition about communication, where information seems tied to how many signals are sent, not to how each one is structured. When orbital angular momentum enters the picture, the question sharpens. If light can be twisted into many distinct modes, then each photon may carry more than a binary choice. The stakes rise immediately. For most of the 20th century, optical communication relied on a small set of variables. Intensity could be turned up or down. Frequency could be shifted. Polarization could be chosen between two orthogonal states. These options worked well. They still do, but they are limited. Polarization offers only a small alphabet. Two states are clean, more quickly become fragile. Orbital angular momentum appeared to offer something different. Unlike polarization, which is constrained to a few stable options, OAM modes form a ladder of states labeled by integers. In principle, there is no upper bound. A photon can carry 1 unit of orbital angular momentum, or 10, or 100, depending on the phase structure of the mode. Each value represents a distinct channel. This possibility caught the attention of communications researchers almost immediately. If multiple OAM modes could be transmitted simultaneously on the same frequency and polarization, then data capacity could increase dramatically. The idea was known as multiplexing, multiple signals, one beam. The promise was clear. The difficulty was not yet visible. Early demonstrations were encouraging. In controlled laboratory settings, researchers generated several OAM modes at once, combined them, transmitted them over short distances, and separated them cleanly at the receiver. Each mode carried an independent data stream. The physics worked. The math was sound. The detectors could tell modes apart. The challenge emerged as soon as the beam left the laboratory. Light traveling through air encounters turbulence, temperature variations, pressure gradients, and wind create fluctuations in refractive index. These fluctuations distort phase. For ordinary beams, the result is blurring or beam wander. For OAM beams, the effect is more subtle and more damaging. The phase structure that defines each mode begins to mix with others. This mixing does not destroy angular momentum. Conservation laws still apply. What it destroys is mode purity. A photon prepared in one OAM mode may arrive in a superposition of many. The information is no longer cleanly separated. Crosstalk appears between channels. Researchers quickly learned that OAM communication is not limited by photon count, but by control. Maintaining phase structure over distance is the central challenge. Adaptive optics, originally developed for astronomy, became essential tools. Systems that measure wavefront distortion and correct it in real time can partially restore mode purity. The same techniques used to sharpen images of distant stars were repurposed to protect information encoded in twisted light. NASA and ESA have long experience with such corrections. Space-based telescopes rely on precise wavefront control to maintain image quality. Interferometric missions demand phase stability across large baselines. The lessons learned there apply directly. Phase matters because structure matters. Detectors present another limitation. Distinguishing OAM modes requires devices that can resolve phase structure, not just intensity. Mode sorters map different OAM values to different positions or signals. Their efficiency and accuracy set practical limits. Imperfect sorting leads to errors even when the beam arrives intact. Quantum communication adds a further layer. In quantum key distribution and related protocols, information is often carried by single photons. Encoding information in OAM expands the available state space. A single photon can represent more than a binary choice. This increases information density, but also increases sensitivity to noise. Experiments have demonstrated quantum entanglement between photons carrying orbital angular momentum. Measurements show correlations that exceed what polarization alone can provide. The results are robust in the laboratory. They become fragile over distance. Again, the physics holds. The environment intrudes. The phrase, twisted light, sometimes obscures this balance. The twist itself is not the advantage. The advantage lies in the number of distinguishable modes that can be prepared and reliably measured. OAM is valuable because it expands the mode space. Mode purity decides whether that expansion can be used. This brings the discussion back to fundamentals. Information in physics is not abstract. It is tied to physical distinctions that can be prepared, preserved, and measured. Polarization offers a small set of robust distinctions. OAM offers a large set of delicate ones. The trade-off is unavoidable. Historical perspective helps here. Radio communication faced similar challenges in its early days. Increasing bandwidth required controlling interference, noise, and channel separation. Optical OAM communication faces its own version of that problem, with phase replacing frequency as the fragile resource. Researchers have explored hybrid approaches. Polarization and OAM can be combined. Frequency and OAM can be layered. Each additional degree of freedom adds capacity and complexity. The goal is not maximal twist, but optimal balance. Measurements show that even modest OAM alphabets can provide advantages in controlled environments. Short-range links, fiber-based systems with specially designed cores, and free-space links with adaptive correction all show promise. None violate fundamental limits. All respect conservation laws. The role of fibers deserves special mention. Standard optical fibers scramble OAM modes due to imperfections and coupling between modes. Specialized fibers with ring-shaped cores and tailored refractive index profiles can preserve OAM over longer distances. These designs reflect the same lesson seen everywhere else. Geometry determines fate. Throughout this development, theory and experiment advanced together. Predictions about mode mixing, turbulence effects, and detector limitations were tested and refined. No hidden capacity appeared unexpectedly. No paradox emerged. The performance matched the physics. Carl Sagan often cautioned against confusing possibility with practicality. He wrote, Extraordinary claims require extraordinary evidence. In the case of OAM communication, the evidence supports possibility, bounded by engineering reality. Twisted light can carry more information per photon, but only when its structure survives the journey. This does not diminish its importance. It clarifies it. OAM is not a replacement for existing communication methods. It is an addition. It expands the toolbox. It forces a deeper understanding of how information rides on physical structure. The deeper lesson extends beyond communication. Whenever angular momentum is encoded in light, the ability to extract it depends on resolving the right features. Intensity measurements see energy. Phase-sensitive measurements see structure. Mode-resolved measurements see information. As experiments continue, the boundary between optics and information theory grows thinner. Twisted light sits precisely on that boundary. It reminds us that photons are not identical carriers differentiated only by arrival time. They are structured excitations of a field. That structure can be used, or it can be lost. As angular momentum, pressure, and mode structure coexist within the same beam, light operates simultaneously as a mechanical agent and an information carrier. In this regime, momentum flow and information flow are no longer separable in practice, because both are transported through the same physical degrees of freedom. That convergence becomes critical in the next part, where the measurable reality of radiation pressure is set against the limits of human sensation and everyday experience. Part 9. If light carries momentum and pressure, why don't we feel sunlight pushing us back? Sunlight strikes your skin every day, yet nothing about the sensation suggests a push. That absence is deceptive. According to electromagnetic theory, every photon arriving from the sun carries momentum, and when it is absorbed or reflected, that momentum must be transferred. The force is real. The pressure exists. The puzzle is not whether it happens, but why it remains so completely unnoticed. The idea that light carries momentum was not obvious when it was first proposed. In the 19th century, James Clerk Maxwell showed that electromagnetic waves transport energy and momentum together. From his equations emerged a quiet prediction. If light carries momentum, then it must exert pressure when it strikes matter. This was not speculation. It was a direct consequence of the theory. Early experiments struggled to confirm it because the effect is small, very small. The momentum carried by a photon is proportional to its energy divided by the speed of light. Sunlight delivers enormous energy over time, but each individual photon carries an almost negligible amount of momentum. When spread across a human body, the resulting force is drowned out by gravity, air pressure, and even the subtle movements of muscles and blood. To understand the scale, it helps to anchor the idea in measurement rather than intuition. At Earth's distance from the Sun, the solar energy flux is about 1,360 watts per square meter. That sounds large. It heats surfaces efficiently, but when converted into pressure, the result is only a few micronewtons per square meter for absorbed light. For reflected light, the pressure doubles, reaching only a few micronewtons per square meter more. This doubling is important. When a photon is absorbed, it transfers its forward momentum and stops. When it is reflected, its direction reverses, and the change in momentum is twice as large. Mirrors feel twice the push of black surfaces. The effect is real and predictable. So why is it invisible to us? Because gravity is overwhelming by comparison. The weight of a human body corresponds to forces measured in hundreds of newtons. Sunlight pushes with forces millions of times smaller. Even a gentle breeze exerts far more pressure on your skin than sunlight ever will. Yet there are circumstances where radiation pressure becomes measurable, even decisive. In carefully controlled laboratory conditions, torsion balances and microcantilevers can detect forces far smaller than anything a human could feel. These instruments confirmed Maxwell's prediction directly. Light pushes. The story does not end in the laboratory. In space, the balance of forces changes. Gravity weakens with distance. Atmospheric drag disappears. Over long timescales, small forces accumulate. This is where radiation pressure leaves the realm of curiosity and enters engineering. Solar sails are the most direct expression of this idea. A large, lightweight reflective surface deployed in space experiences a continuous push from sunlight. The force on any small patch is tiny, but spread over thousands of square meters and applied continuously, it becomes useful. Spacecraft accelerate slowly, steadily, without fuel. NASA and other space agencies have tested this principle in practice. Missions, such as Icaros and experimental solar sail demonstrators, showed that sunlight alone can alter trajectories measurably. The sails do not leap forward. They drift, gaining velocity over weeks and months. The physics is identical to what Maxwell described. Only the environment has changed. Radiation pressure also plays a role in shaping the small bodies of the solar system. Dust grains near stars feel competing forces. Gravity pulls them inward. Radiation pressure pushes them outward. For sufficiently small particles, the push can rival or exceed gravitational attraction. This effect helps explain the structure of comet tails and the distribution of dust around stars. Astronomers account for radiation pressure when modeling stellar environments. In massive stars, intense radiation fields can drive stellar winds, pushing matter outward from the star's surface. These processes are observed and measured using space-based observatories operated by agencies such as NASA and ESA. The momentum carried by light shapes astrophysical systems on vast scales. Back on Earth, textbooks often present radiation pressure as a formula, a line at the end of a chapter, but the deeper message is conceptual. Momentum flow is inseparable from energy flow. Whenever energy moves through space in the form of electromagnetic waves, momentum moves with it. The two cannot be separated. This connection explains why radiation pressure is closely tied to angular momentum as well. If light carries linear momentum, it can push. If it carries angular momentum, it can twist. The same photons responsible for a tiny push are also responsible for torque when their structure allows it. The reason we do not feel sunlight pushing us back is therefore not that the push is absent, but that our senses are tuned to much larger forces. Evolution did not prepare us to notice micronewton pressures. Physics, however, does not care what we notice. It cares what can be measured. In precision experiments, radiation pressure becomes a limiting factor. Laser interferometers, designed to detect gravitational waves, for example, must account for the pressure of photons bouncing between mirrors. At extreme sensitivities, photon momentum introduces noise and subtle shifts. Engineers design around these effects, treating light not just as a probe, but as a participant. This perspective reshapes the familiar picture of light as something that merely illuminates. Illumination is energy delivery. Momentum delivery comes along with it, quietly, relentlessly. Whether it matters depends entirely on context. Carl Sagan often emphasized that nature's most important effects are not always those we feel directly. He wrote, "The surface of the Earth is the shore of the cosmic ocean. On that shore, sunlight warms and brightens. Beyond it, the same sunlight pushes, twists, and sculpts matter across space." The absence of sensation does not imply absence of cause. A person standing in sunlight is held in place by forces far stronger than radiation pressure. Remove those competing forces, and the push reveals itself. There is also a lesson here about scale. Physics does not privilege human perception. Laws apply equally to dust, grains, spacecraft, mirrors, and people. The difference lies in relative strength. Radiation pressure is weak, but it never switches off. Over time, that persistence matters. Understanding why we do not feel sunlight pushing us back helps clarify a broader theme running through this series. Light carries momentum in multiple forms. Linear momentum produces pressure. Angular momentum produces torque. Phase structure redistributes both. The effects are always present. Their visibility depends on circumstance. This grounding prepares the final step. If light can push, spin, trap, and carry information, then the simple image of the photon as a point-like particle or a featureless wave begins to strain. The accumulated evidence points toward a richer picture, one where structure, momentum, and measurement are inseparable. Across these observations, light exhibits rotation, pressure, and information transfer within the same physical entity. These behaviors do not separate cleanly into wave or particle descriptions, but coexist within a single framework that must account for structured momentum and measurable interaction. At this boundary, the physical character of the photon becomes the only remaining element capable of unifying all of these effects without contradiction. Part 10. After all this, is the photon a point, a wave, or a structured packet with real geometry? After everything that has been measured, twisted, trapped, and counted, one simple picture finally breaks. Light cannot be reduced to a featureless point racing through space, and it cannot be fully captured as a smooth wave spread everywhere at once. Every experiment we have followed presses against those limits, until a more careful description becomes unavoidable. The photon reveals itself only when structure is taken seriously. For much of the 20th century, physics alternated between two useful models. In some experiments, light behaved like a wave, producing interference, diffraction, and smooth energy flow. In others, it behaved like a particle, delivering energy and momentum in discrete packets. Both models worked. Neither was complete. What this series has shown is that the tension between them dissolves when geometry enters the discussion. Spin angular momentum was the first clue. Circular polarization was not a visual preference. It carried a conserved quantity. Matter rotated because the electromagnetic field rotated in time. This was not metaphor. It was torque measured on torsion fibers and trapped particles. The photon carried spin, not as a tiny spinning object, but as a consequence of field symmetry. Orbital angular momentum extended the lesson. Light could twist without polarization changing at all. Phase structure alone was enough. Vortex beams carried angular momentum because their wavefronts were arranged in space with a definite winding. Particles orbited because momentum flowed sideways as well as forward. The effect depended on geometry, not on intensity or mass. Optical tweezers made momentum flow tangible. Light pushed, pulled, held, and spun matter in ways that could be tuned and measured. Radiation pressure, once a textbook footnote, became a design constraint and a tool. The same photons that illuminated also exerted force. Single photon experiments closed the loop. Even when light arrived one quantum at a time, angular momentum transfer occurred in fixed units. The smooth field picture survived statistically. The discrete picture governed each exchange. There was no contradiction. The descriptions met cleanly at the boundary defined by measurement. By this point, the question about what a photon is could no longer be postponed. A point particle cannot carry spatial phase structure. A simple wave cannot explain discrete torque events. The evidence points instead to a structured excitation of the electromagnetic field, one that occupies a mode with definite geometry. Quantum electrodynamics provides the language for this description. In that framework, photons are not objects with size or shape in the ordinary sense. They are excitations of field modes. Each mode has a spatial structure, a frequency, a polarization, and well-defined conserved quantities. Angular momentum belongs to the mode. The photon inherits it by occupying that mode. This explains why changing the mode changes the behavior of light without changing its energy. A photon in one spatial mode can push differently, twist differently, and carry information differently than a photon in another. The energy may be the same, the geometry is not. Experiments confirm this view repeatedly. Mode sorters separate photons by orbital angular momentum. Interferometers reveal phase winding. Detectors register torque consistent with mode structure. None of these outcomes depend on imagining a photon as a tiny bead. They depend on treating it as a structured field excitation. This perspective also resolves familiar confusions. Asking whether the photon is a wave or a particle becomes less useful than asking which properties of the field are relevant to a given measurement. When interference is measured, wave behavior dominates. When energy and momentum are exchanged, particle-like discreteness appears. When angular momentum is involved, geometry becomes decisive. The most honest picture depends on what you build and what you measure. A wave plate measures spin. A vortex beam reveals orbital angular momentum. A torsion balance records torque. An optical trap maps momentum flow. Each instrument selects a different aspect of the same underlying entity. NASA and ESA instruments operate under this principle daily. Space telescopes rely on wave descriptions to form images. Photon counting detectors rely on particle descriptions to register faint signals. Interferometers depend on phase coherence across large distances. None of these descriptions contradict one another. They overlap where needed. Carl Sagan often reminded his audience that science advances by refining questions, not by clinging to comfortable images. He wrote, "We are a way for the cosmos to know itself." In studying light, that self-knowledge has required abandoning the idea that one picture must rule all others. What remains after this journey is not a single model, but a disciplined way of choosing among them. Light is best understood as a structured carrier of energy, momentum, and information. Its behavior follows from field geometry constrained by quantum rules. The photon is neither a point nor a smear. It is an excitation with internal organization. This understanding does not weaken earlier theories. It strengthens them. Maxwell's equations describe the field. Quantum theory describes its excitations. Conservation laws bind them together. Angular momentum, once thought to belong only to spinning matter, flows naturally through this unified picture. There is also a practical consequence. As optical technologies advance, engineers increasingly design light by shaping modes rather than increasing power. Communication, sensing, manipulation, and measurement all depend on structure. The geometry of light becomes a resource. At the end of this path, the original discomfort dissolves. Light twists because it has structure. It pushes because it carries momentum. It can be counted one photon at a time because energy and angular momentum are exchanged discretely. None of these facts stand alone. They reinforce one another. The photon, then, is best seen not as an answer, but as a bridge. It connects waves and particles, fields and forces, geometry and measurement. The bridge holds because every experiment we have followed steps onto it from a different side and finds it solid. As this series settles, there is no need to force light into a final picture. What remains is what measurement has shown, carefully and patiently, through tools built to listen to nature on its own terms. The structure is real, even when it stays out of view. If you've been here through this long exploration, thank you for sharing your time and attention. That presence matters more than it might seem. You can let the world continue its quiet work around you without needing to follow it any further tonight. I hope this hour has given you a steady place to rest. Wherever you are, May the night treat you kindly. And if you'd like to stay close for future journeys like this, a gentle subscribe is a simple way to do that. Good night.